Okay. Yeah.
I think, welcome everyone. Welcome to the very exciting winter mini course. And this is given by Dr. Ravenel from Rochester University. And the topic is telescope conjecture, focus on the introduction and how it was raised by Dr. Ravenel.
Well, thank you, Guchuan. Thank you, Dan, for the invitation to do this. I think it was a good idea. And thank you all for coming. I'm going to share my screen now. This first lecture is going to be mostly algebra having to do with MU theory and formal group laws, which are things you need to understand in order to follow chromatic homotopy theory. So I'm going to begin talking about the space BU, which is the classifying space for the stable unitary group U. This is a space that's been very well understood for a long time. Somebody, I forget who, said its homology is one of the most beautiful objects in mathematics, and I have to agree with that. So it's the classifying space for the stable unitary group U. That means that it's the stable unitary group is the co-limit of all the UNs, and it's also the classifying space for complex vector bundles. And among complex vector bundles, there's a Whitney sum map, and that leads to a map from BU cross BU to BU. It makes BU into an H space with a lot with it. This multiplication is commutative in the strongest possible sense. And it induces a ring structure on the homology. And so the homology now is a graded ring. Now you're probably accustomed to the cohomology of a space being a graded ring, and that's certainly true, but that cohomology ring structure is not relevant to our purposes, but the homology ring structure is very relevant. So the structure of this graded ring in homology it's a polynomial algebra over the integers with generators denoted by B1, B2, and so forth. And the dimension of BI is 2i. And each of these BIs has a very geometric definition that goes like this. You can look at the homology of CP infinity, and in so that's the homology of CP infinity is the integers in every even dimension, and there's a canonical way to define the generator of that group, and I'm going to call it beta I. And there is CP infinity is the classifying space for U1, and which is the circle group. And so there's a map from BU1 to BU, and each BI is the image of the generator beta I. And the best reference for this material is the book of Milner-Stasheff on characteristic classes that was published in 1974. Now, I can tell you what the how the homology of BUN sits inside of this. It is not a subring. But what you can say is that the image in homology is spanned by monomials in those B's of degrees less than or equal to n. That gives you a description of the homology of BUN. Now we also have a geometric description of the space BUN. It's the Grassmannian of complex n-planes in an infinite dimensional complex vector space that I'm calling C infinity. And it's the classifying space for n-dimensional complex vector bundles. And the total space, there's a universal complex n-plane bundle over it. And the total space is the following. There is, we're looking at points in the product BUN cross C infinity where the vector in C infinity lives in the n-plane corresponding to the point X in BUN. So that is the total space of a vector. So there's a map from that to BUN where you just forget about the second coordinate, and the pre-image of each point is the n-dimensional subspace of C infinity that corresponds to the point in BUN that you're looking at. Now, if we collapse all the points where the length of the vector v is greater than or equal to 1, if we collapse all that to the single point, we get something called the tome space, MUN. And we know that its homology is isomorphic to that of BUN, but it's shifted up by 2n dimensions. So in other words, HK of BUN is isomorphic to HK plus 2n of MUN. And furthermore, we can, if we consider the universal n-plane over BUN plus 1 and restrict it to BUN, what we get is the direct sum of the universal n-plane bundle, which I'm denoting by gamma n upper C, and a trivial line bundle, which I'm denoting by epsilon 1 upper C. Now, the tome space for that gadget is the double suspension of MUN. So we get a map from the double suspension of MUN to MUN plus 1. And that we can assemble all these into a spectrum called MU. So I'm thinking of a spectrum as a sequence of spaces with maps from the suspension of one space to the next space. And the 2nth space in this spectrum is the tome space MUN, as I've just defined it. And the 2n plus 1 space is the suspension of MUN. And that defines all the spaces in this spectrum. So we get a spectrum MU, and it turns out that it has an E infinity ring structure, which is very nice. And it's, in fact, it's one of the nicest spectra you'll ever meet. And it gives us a very good tool for computing the homotopy groups of spheres, namely the Adams-Novikov spectral sequence, which is the subject of the book that I published in 1986 that I'll refer to as the Green Book. So we need to know some things about this spectrum. So it has a lot of very nice properties that I'll talk about now. Are there any questions so far? Okay, please stop me if there are any questions. So first of all, the homology of the spectrum is the same as the homology of the space BU by the tome isomorphism. It's again, it's a polynomial algebra on classes B sub I that live in dimension 2I. We also know the homotopy of the spectrum. It is again a polynomial algebra on even dimensional generators that I'll denote by xi. They are not the same as the bi's. And this was proved independently by Milner and Novikov around 1960. If we localize the spectrum at a prime p, then it splits into a wedge of suspensions of an infinite wedge of suspensions of a much smaller spectrum called BP, which stands for Brown and Peterson. And the homotopy of BP is a polynomial algebra where the dimensions of the generators are as indicated here. They're far fewer. Instead of a generator in every even dimension, we only have generators in dimensions which are 2 less than twice a power of p. And you can do this for any prime p. BP, as I said, is the Brown-Peterson spectrum first constructed in 1966. Now, MU lower star MU, that's the homotopy of MU smash MU. or the MU homology of MU itself is this gadget. It's a polynomial algebra on the BIs over pi star of MU, which I'm denoting by MU lower star. And the pair consisting of MU star and MU star of MU forms a Hopf algebroid that I'll say more about later. In particular, I'll say later what a Hopf algebroid is. And this gadget was first studied by Novikov and Landweber in the late 60s. MU star, the homotopy of this spectrum, is also the complex cobordism ring by a theorem of Thom. So for each closed n-dimensional complex analytic manifold V, there's an element that I'll denote by bracket V in this cobordism ring that is represented by this manifold V. Now, recall that MU star is a polynomial algebra on even dimensional generators, x1, x2, and so on. We do not have convenient descriptions of these generators, but we can say the following. If we tensor this ring with the rationals, it is isomorphic to the polynomial algebra generated by the cobordism classes of the complex projective spaces, CP1, CP2, and so on. Here's some more things about it. There is a cohomology theory associated with MU, and its value on CP infinity is a power series ring on a single variable of dimension 2. Now, MU upper star means MU upper star of a point. That is a negatively graded version of MU lower star. So it's a polynomial algebra with a generator in every negative even dimension. And this gadget, this power series ring, is the limit over over the cohomology of the CPMs. You take the so CP infinity is the co-limit of the finite dimensional projective spaces CPM. The cohomology of CPM is the truncated polynomial algebra on X that you see here. And so you take the limit of all those things, you get the power series ring on X. Similarly, you can describe the cohomology of the product CP infinity cross CP infinity as a power series ring on two variables that I'll denote by X tensor 1 and 1 tensor X. Now, CP infinity is the classifying space for complex line bundles. And if you have two complex line bundles, you can take their tensor product and get another one. So that means there is a map from CP infinity cross CP infinity to CP infinity. And I'm drawing the arrow pointing to the right and pointing to the left instead of the right for a reason, which you'll see in a moment. So CP infinity itself is an H space, and it has a structure map that corresponds to tensor product of complex line bundles. So what I'm interested in is how this map behaves in MU cohomology. So in cohomology, we get a map going the other way. So there's a map from MU upper star of CP infinity to MU upper star of CP infinity cross CP infinity. So that's a map from a power series ring on one variable to a power series ring on two variables. And that is that's determined by its image on X. And that image is a certain power series ring, a certain power series in the two variables that's denoted by summation aij x to the I, y to the j. And aij lives in this group. It has dimension twice 1 minus I minus j. And the sum is over all non-negative I and j, with the stipulation that I plus j has to be at least 1. So the sum is a homogeneous expression of dimension 2. Remember, the x to the I has dimension 2i, x to the j has dimension 2j, and when you add that to this dimension here, you get 2. So this thing is a homogeneous expression of dimension 2. Now, it turns out that there is a great deal of information in this power series. It turns out that this power series is the linchpin of the theory in ways that I'm going to describe. So this power series is easily seen to have the following three properties. One is that if you make either of the variables equal to 0, then you get x. 2, okay, so this means in particular that this means that the AI0 is determined, AI0 and A0I is determined by this formula. Secondly, there's a commutativity condition. F of yx is the same as f of xy. And third, so that means the coefficients aij have satisfy this symmetry condition. Third, there's an associativity condition that says well, it's written here. I won't try to say it out loud. Anyway, there's an associativity condition. Now, these three conditions on the power series follow from three corresponding conditions on complex line bundles. The tensor product of complex line bundles is associative, commutative, and unital. And that leads to these three conditions on the power series. Now, the last of these conditions implies complicated relations among the AIJs that are hard to write down. Now, a power series over a ring, over a general ring R that satisfies these three conditions is called a formal group law over R, or a one-dimensional formal group law. Now, it turns out that we know a lot about formal group laws. And properties of formal group laws, I'm going to spend the next few slides talking about formal group laws because their properties turn out to have implications in homotopy theory. So the next part of this lecture is just going to be pure algebra. It's about what we know about formal group laws, about power series and two variables that have these three properties. So first, I'm going to give you some examples of such things. Now, the simplest example is called the additive formal group law. In that case, the power series is simply x plus y. Now, that certainly satisfies the three conditions. We know that addition is commutative and associative and unital. The next example is something called the multiplicative formal group law. So it's x plus y plus xy. And you should note that if you add 1 to it, you get the ordinary product of x plus y, 1 plus x and 1 plus y, and that makes it easy to verify the associativity condition. Now, so far, so these two examples, the power series, in these two examples, the power series are actually polynomials. The next two examples, that is not the case. So here's another one. This is what I call the tangent formal group law. So f of xy is x plus y divided by 1 minus xy. That has a formal power series expansion, which you can easily work out. And that guy is known as the tangent formal group law. Let me remind you of a trig identity that says the tangent of the sum of two angles is F of tangent alpha tangent beta. That's a trig identity that they should have taught you in high school. Now, I'm going to give a fourth example, which you may not be familiar with. This is something that Euler discovered in studying elliptic integrals maybe almost 300 years ago. Anyway, this thing is a power series over Z bracket a half. Now, it's not obvious here that this is associative, but you can check it, and it is. Now, Michel Lazard studied formal group laws in 1955, and he considered the ring Z bracket Aij, where the Aij's are the same as the Aij's in the Aij's that occur in an arbitrary formal group law. And I want to take the polynomial algebra generated by these Aij's and mod out by certain relations, namely the relations that are implied by the three defining properties of the power series f of xy. Now, as I noted before, two of those three properties, the unital condition and the commutativity condition, lead to very easy conditions on the Aij's, but the associativity law leads to very complicated relations on the Aij's. And so it's not at all clear what this quotient is, what this quotient ring actually is, and Lazard figured it out. But before I get into that, let me point out that any formal group law over any ring is induced from this formal group law, which I'm calling G, by a ring homomorphism theta from L to R. So the L, this Lazard ring L, is the thing over which it's the ground ring for the universal formal group law. So it's universal in the sense that any formal group law over any ring R is induced from this one by some homomorphism that I'm calling theta from L to R. Now, to describe this ring L, I'm going to give it a grading which is consistent with the grading that on the complex cobordism ring mu upper star. So each of these Aij's, each Aij is going to get dimension 2 times 1 minus I minus j as before. Then it turns out that the structure of L is that it's a polynomial ring on on generators in negative even dimensions. Now, each of these xi's is a certain can be described is a certain polynomial in the Aij's, but it's hard. There isn't a convenient way to describe them. But anyway, Quillen noticed that if you consider the formal group law over mu upper star that's related to the tensor product of complex line bundles, there will be a map that will be induced by a map theta from L to mu star, and that map is an isomorphism. In other words, the formal group law that we have over mu star that was defined in terms of tensor product of complex line bundles, that is in fact the universal formal group law. Now, this means that homotopy theorists are married to one-dimensional formal group laws. Now, I'm going to talk about some more things you can do with formal group laws. Let me get this thing out of the way. If you have a formal group law, there's a bunch of power series associated with it called bracket n sub f of x, so for each natural number, there's a power series called the n series for f. And these are defined recursively as follows. For bracket 0 of X is simply 0. And then bracket N is defined inductively as F of X, comma, bracket N minus 1 of X. So this is an inductive definition. Bracket 1 of X is X, bracket 2 of X is F of X, comma, X, and so on. And so here's some examples of this in the case of the additive and multiplicative formal group laws. In the additive formal group law, bracket N of X is simply N times X. In the multiplicative case, it's a sum involving binomial coefficients, or in other words, it's the nth power of 1 plus X minus 1. You subtract 1 from the nth power of 1 plus X, and that's what this polynomial is here. Now, we are particularly interested in the P series. For pick a prime P, we've got the P series, and we want to look at it. We want to look at its image in R mod P for each prime P. Now, if R mod P happens to be a field, then it's known that the power series bracket P of X is either 0, or it's a power series in which the leading term, the exponent of the leading term, is some power of P to the H. So that so the power series has the form A x P to the H plus higher terms, where A is some non-zero element in this field. Now, this exponent H is called the height of the formal group law. So if this P series is 0, we say the height is infinity. Otherwise, it's the exponent H that you see here. And when R has characteristic 0, we can talk about its heights at the various primes that are not invertible in it. Now, here's how this plays out in the examples that we've looked at before. For the additive formal group law, its height is always, the height of that at any prime is infinite, because the P series at any prime is 0, as I said before. In the multiplicative formal group law, it turns out that it has height 1 at all primes. The tangent formal group law that I mentioned before has infinite height at the prime 2, but it has height 1 at all odd primes. And finally, this Euler's formal group law, which was defined over Z bracket a half, has height 1 or 2, depending on whether the prime is congruent to 1 or 3 mod 4. If the prime is congruent to 1, the height is 1. If the prime is congruent to 3, then the height is 2. And the height at the prime 2 isn't defined because 2 is invertible in that ring. That means if you tried to reduce mod 2, you get 0. So the height at the prime 2, in this case, is not defined. Are there any questions? All right. Moving on, Lazard proved that two formal group laws over the algebraic closure of FP are isomorphic if and only if they have the same height. In other words, the height is a complete isomorphism invariant over the algebraic closure of FP. Now, Jack Morava realized that this has profound implications in homotopy theory, and I'll say a lot more about that later. But anyway, Lazard proved that you can classify formal group laws over FP bar by their height, and it turns out that this has profound implications in homotopy theory. Now, In addition, Lazard described the automorphism group in each case, the automorphism group over FP bar of a height H formal group law. And this is a compact p-adic Lie group now known as the Morava stabilizer group. And we now know that there are elements of V sub H in that Lazard ring L that have the dimension indicated, such that the height of a formal group law induced by a homomorphism theta from L to R is the smallest H for which theta of VH is non-zero mod P. That number is that is the height of the formal group law. It's related, the height of the formal group law is related to how these particular elements get mapped to R mod P. Now, let's consider the ideal I sub H generated by V0, V1, etc., where V0 is understood to be P. Then there's an ascending chain of ideals, I1 contained in I2, contained in I3, and so on. And that ascending chain of ideals is related to the chromatic filtration in stable homotopy theory that I will discuss. I'll say a lot more about this later. Anyway, the basic algebra underlying the chromatic filtration is this ascending chain of ideals in the Lazard ring L. Now, you might ask, well, this is all very nice, but you might ask, are there formal group laws of heights greater than 1 or 2? I've yet to show you an example. Now, a formal group law of height, not only so that Honda in 1970, the Japanese number theorist Taira Honda constructed a formal group law for which the P series is exactly x to the P to the H. So that means all formal group laws occur. Now, I'm going to read you the fine print on this billboard. I find this billboard very amusing. It was created by Yuri Salima. It was part of the Facebook page called Derived Memes for Spectral Schemes or something like that. Anyway, it says, you meet the nicest people on a Honda formal group. Maybe it's the incredibly simple P series, or the fact that they give a canonical way to construct formal group laws of every height, or it could be that they're carried by the 2 periodic versions of Morava K-theory, using the universal deformation to construct Morava E theory will make you feel right at home too. But most likely it's the fun. Evidently, nothing catches on like the fun of chromatic homotopy theory. You see so many Honda formal group laws around these days, and the nicest people are writing them. Merry Christmas. For the address of your nearest dealer or other information, write Jack Morava, Johns Hopkins University. Now, let's say you have 2 formal group laws, F and G, over a ring R. You can ask about a homomorphism between them. So a map between them is a power series F of X, little f of X, that has this property. If I take G of F of X, little f of X, comma, f of Y, that should be the image of big F of XY under little f. So a map between formal group laws is a power series little f that has that property. Now, this power series will be an isomorphism if f prime of 0, meaning the linear coefficient in the power series, if that linear coefficient is a unit in the ring over which the power series is defined, over which the formal group laws are defined. It'll be an isomorphism if that coefficient is a unit, and it's called a strict isomorphism if that coefficient is 1. Now, a logarithm is a strict isomorphism to the additive formal group law. Now, there's a theorem that says the following. Let's say F is a formal group law over R. Let's say R is in characteristic 0. Now, we define a power series little f by this formula that involves an integral. Now, this is a power series with coefficients in R tensored with the rationals. You have to tensor with the rationals because when you integrate a power series, you end up dividing by the exponents. You have to pass from R to R tensor Q. Now, so this is a certain power series associated with a formal group law over a ring R in characteristic 0. Now, then this F is a logarithm for big F, meaning that big F of xy is the same thing as little f inverse of little f of x plus little f of y. And this means that big F is isomorphic over R tensor Q to the additive formal group law. So once you tensor with Q, all formal group laws become isomorphic to the additive one. So this is a very different situation from characteristic P. So in characteristic 0, if you tensor with Q, all formal groups are isomorphic to the additive one. In characteristic P, you have countably many distinct isomorphism classes of formal group laws. Okay, here's the theorem again. Now, I can give you a reference for the proof. It's stated as a certain theorem in the Green Book, and the proof is actually a calculus exercise, as explained there. Now, so we could apply this to the formal group law over complex it's defined over complex cobordism, and in that case, I'm going to tell you what power series we get, what the logarithm is. So here it is. It's a power series in which the coefficient of x to the n plus 1 is the cobordism class of the n-dimensional complex projective space, CPN, divided by n plus 1. So that result is known as Mashenko's theorem, and it's in Novikov's 1967 paper. Okay, so this is Mashenko's theorem. Now, there's an analogous formula in BP theory that goes like this. In BP theory, the logarithm has a similar description, except there are many fewer terms. The only exponents of x that occur here are where the exponent itself is a power of p. And so, in other words, this power series has far fewer terms than this power series up here. And this is the logarithm in BP theory. Now, I mentioned before that pi star of BP was a polynomial algebra on those V's. So there is a relation between the L's that appear in this series right here and those V's, and it's a formula due to Hazewinkel, and this is it. This is a recursive formula, and I'll give you a couple of examples of it on the next slide. So here are the first few of them. L1 is V1 over P. L2 is V2 over P plus V1 to the P plus 1 over P squared, and so on. So these are formulas that relate the L's. Now remember, each L is a projective space of the L sub k is a projective space of the appropriate dimension divided by P to the k. And the L's and V's are related by this formula. Now, recall that the height of a formal group law over a ring of characteristic P is the smallest h, such that V sub h has a non-trivial image under the homomorphism from L to R that induces F. Now, are there, nobody said a word. Are there any questions? All right, I'm going to give you examples of logarithms. So for the additive formal group law, remember the logarithm is meant to be an isomorphism over the rationals between the formal group law that you have and the additive formal group law. So if we're starting with the additive formal group law, that means the logarithm is simply x. The logarithm is a power series in one variable, and in this case, it's simply x. Now, for the multiplicative formal group law, the logarithm turns out to be this. This is the power series for the natural log of 1 plus x, something you teach to your calculus students. In the case of the tangent formal group law, the logarithm is the arctangent function, which is this power series. In the case of Euler's formal group law, there is an explicit formula for the logarithm of that thing, and here it is. Finally, for Honda's formal group law, the logarithm is this. All right, now we want to set up and study atom spectral sequences based on MU and BP theories. And this means that we have to have a working knowledge of the structures of these gadgets, MU star MU and BP star BP. These are the analogs of the dual Steenrod algebra in ordinary mod P homology. And we have to understand them very well in order to set up an atom spectral sequence. Now, I'm not going to get into the nuts and bolts of these two objects. They are thoroughly described in the Green Book. And what I'm going to do here is instead present a conceptual picture of them. So this conceptual picture involves groupoids. Now, a groupoid is a small category C in which each morphism is invertible. That's what a groupoid is. In particular, if you have a groupoid, if you have such a category with one object, that's the same thing as a group. You can think of a group as a category with one object, and in which every morphism is invertible, and the morphisms are the elements of the group. But anyway, if you have a groupoid, there are two sets associated with it. There's a set of objects, which I'm calling OBC, and there's a set of morphisms that I'm calling MORC. And there are four maps between them that go like this. So for each object, there is an identity morphism. So that gives you a map from OBC to MORC, from the set of objects to the set of morphisms. Each morphism has two objects associated with it, namely the source and its target. So source and target are maps from the morphism set to the object set. And there's a map from the morphism set to itself, which assigns to every morphism to its inverse. Remember, every morphism in this category is invertible. Now, these four maps satisfy some obvious identities that I'm not going to write down, but they're obvious. Now, there's one more piece of structure, and that is composition of morphisms. So what is that? If you have two morphisms where the source of one is the target of the next, you can compose them. And so those are called composable pairs of morphisms. And the composable pairs of morphisms are the pullback. It's a certain subset of Morse cross itself, namely the pullback of this diagram. So you've got the target map from the morphism set to the object set, and the source map from the morphism set to the object set. And you look at the pullback of that diagram, and that is the set of composable pairs of morphisms. So there's a map from that to the morphism set, and that's composition. And that also has to play nicely with the other four maps that I described above. There are certain, so that's a fifth map. And there's, as I said, there are certain identities involving these five maps that are obvious. Okay, so that's what a groupoid is. A groupoid is a small category in which every morphism is invertible, and there are two sets associated with it, or I guess three sets. There's the set of objects, the set of morphisms, and the set of composable pairs of morphisms. And then there are various maps here between these things, and they satisfy obvious identities. Now, a groupoid scheme over a commutative ring K is a functor that assigns a groupoid to each commutative K algebra R. So it's a functor that assigns some kind of functor that assigns a groupoid to every K algebra. And it's said to be affine if it's representable, meaning it's the set of, well, I'll spell out what that means. An affine groupoid scheme is also called a Hopf algebroid. So what does this mean? This means, remember that a groupoid consists of, it's a small category with invertible morphisms. So there's a set of objects and a set of morphisms. So in this situation, there are K algebras A and gamma that represent the object and morphism sets, such that the object and morphism sets for a K algebra R are the set of K algebra morphisms to R from A and from gamma. So that means there are corresponding maps between A and gamma shown below. Now, this diagram is similar to the diagram on the previous slide, except the arrows are going in the opposite direction. This whole business is contravariant in A and gamma, because we're looking at maps out of A and out of gamma. So the arrows in this diagram are going the opposite direction from the arrows in the diagram on the previous slide, which I'll show you. So in this diagram here, we have the object set and the morphism set, and we have the identity going for every object, there's an identity morphism. For every morphism, there's two objects, namely the source and target, and so on. And now the arrows are going in the opposite direction, but they have to satisfy the same kind of identities. And there's, again, a composition map, which is a coproduct. Composition corresponds to a coproduct map, which goes from gamma to the tensor product of gamma with itself over A, and that tensor product is using the right and left module structures on let's see, gamma is both a left A module and a right A module, given, and that structure is given by these two maps known as the left and right units. Those are corresponding to the source and target maps, or target and source maps in C. And the maps C and epsilon are known as conjugation and unit, or conjugation and co-unit, sorry. So all of this constitutes a Hopf algebroid. Now, the case of interest to us is the following. There's an affine groupoid scheme which assigns to every commutative ring R the category of formal group laws over it and isomorphisms, possibly strict isomorphisms between them. So if you have a ring R, there is a set, there's the collection of all formal group laws defined over it, and you can look at isomorphisms between them. That gives you a groupoid. So the ring representing the object set is the Lazard ring L, because that's the ring over which the universal formal group law is defined. And we know that that ring is isomorphic to mu star. And an isomorphism between formal group laws can be any power series of the form summation bi x to the I plus 1, where B0 is invertible. And in the strict case, we want B0 to be 1. So this means the morphism set is represented by this ring or this ring, depending on whether you want your isomorphisms to be strict or not. And in the strict isomorphism case, this ring is isomorphic to mu star mu. In this case, it's a little bit bigger because you've got this extra invertible element in it, B0. Now, in the late 60s, Landweber and Novikov found explicit descriptions of these structure maps. I'm not going to give them here. You can find them in the Green Book. Now, for computations, it's more convenient to use, if you're doing explicit computations with this, it's more convenient to use BP theory, even though we now know that the spectrum BP is not as nice as the spectrum MU because it does not have as much multiplicative structure. Recall that MU is known to be an E infinity ring spectrum. BP is known not to be an E infinity ring spectrum. That's a theorem of Tyler Lawson, proved sometime in the last 20 years, I forget. BP is not an E infinity ring spectrum. I think it's known to be, it's an E something ring spectrum. I forget what. Anyway, this is not relevant. This lack of finer multiplicative structure isn't relevant for the kinds of computations that we need to do. So this is a description of BP star BP. It's a polynomial algebra over BP star on generators T1, T2, etc. And these T's have the same dimensions as the V's. And then the following formulas are due to Quillen. In order to get nice formulas for the structure maps, you need to tensor with the rationals. So the right unit on the LIs is given by this formula, and the coproduct is given, the coproduct on the T's is given by this recursive formula. Now, admittedly, these formulas take some getting used to, but I'll refer you to the Green Book for how to deal with these formulas. So that's the end of my lecture for today. Thank you.
Hey, yeah, thank you. Yeah, let's first thank Doug for the great talk.